Hello, and now it's time to review what might have been one of the most practical chapters in this book. Length and area comes up all the time. You don't have to be working at any particular job. Around the house, you will need to know things like this. Believe it or not, when it comes time to put curtains up, you're going to have to know how to do some of this. Oh, unless you're rich, and I guess maybe you could hire somebody to come in and do it. I believe there are interior decorators who do that stuff for free. Well, not for free. They do it for you for money. But assuming you don't want to be a slave to other people, you should know about length and area. You shouldn't always have to pay somebody else to do your thinking for you. It's too expensive. First question. You got a dog tied to a leash, so we're experimenting in animal cruelty here. How far can this, what's the area? How much space does this dog have to roam around in this 18-foot radius sector? Well, what's the size of this arc? I think we have an 18-foot radius. We can see that pretty easy. But the dog can't get over here. The shed's in the way. So, and this shed has 90-degree walls here, which means we're just missing this 90-degree sector of the circle. Or this arc is 270 degrees. So all we have to do is take the 270 times 360. That's our fraction of the whole that is made up by this sector. Now, what would the whole thing be? Pi times 18 squared. And that'll give us the large area. So if we do all that, perform the calculations, we should get that, you can save yourself a little trouble by noting right off the bat that 270 over 360 is the same as 3 over 4. 270 is 3 times 90. This is 4 times 90. So if you do that, you can write it in your calculator as 0.75 times pi times 18 squared, and you'll get 763 square feet for this big sector here. Now, the smaller sector, it took me a minute to figure out what the heck they were talking about. They're talking about this part here. Maybe that was immediately obvious to you. It wasn't to me. Because the dog comes all the way around here. Well, the leash is 18 feet. 12 feet of it will be taken up by this. But this part here, he'll have 6 feet left over here, where he can move around at this corner of the shed. And so this whole circle here is, this whole problem reminds me of the Foghorn Leghorn cartoons. The rooster, which is always being chased by a dog, has a line drawn right here. He knows exactly how close he can get to the dog. He can come up here and do anything he wants as long as he doesn't cross that line. So, if Foghorn and Leghorn are doing this, how much room does the dog have to move around in this small sector? Well, again, it's kind of obvious that this is just a straight line from here, right? That this is perpendicular, so this whole thing is just 90 degrees with a 6-foot radius. So what we have to write is 90 over 360. So we just write out the fraction of the whole, which is represented by our sector. That's 90 over 360 times pi times 6 squared. I get 28.26. You may get slightly different answers in the hundredths column if you actually use the pi button on your calculator. I use lots of different calculators. Some have buttons, pi buttons, some of them don't. Some of them take me too long to find. I just don't have the patience to look for it. So I just always use 3.14. And as you know, there's a whole bunch of decimals after that, which with large calculations can cause slight differences in the hundredths. So if you didn't get exactly that, it's probably because you used the pi button and I just used 3.14. Next question, what is the total area over which the dog can move? Well, gee whiz, I don't think you'd even have to take geometry to figure that out. I mean, the total area is this plus this. Most people would not have to see our area addition postulate to assume it. I think most people who never took a geometry class would say, well, if the areas don't overlap and there's no spaces in between, then they must add up to the whole thing. And that, in fact, is our area addition postulate, much like our segment addition postulate. So to get the total area, all we have to do is what probably anybody would do. Add up the two areas, 763 plus 28.26. And that's all you had to do. Add these two up, get 791.26. So all you had to remember to work this problem was really your formula for areas of sectors. And of course, if you forgot the area of an actual circle, that would be a problem. As long as you can remember pi r squared, and remember that the area for the sector is just the same. You just take the fraction of the whole area as the fraction of the sector. If this is 3/4 of the whole, you multiply the whole area by 3/4. If it's 1/4 of the whole, you multiply the whole area by 1/4. Now in this problem they gave us some points that lie on the circumference of a circle, and they asked us to graph the circle. I went ahead and did that. This grid that I've drawn, the horizontal markers are a bit larger than the vertical ones, so I could fit them in. You might be able to see that these vertical tick marks are a bit closer together than the horizontal ones, so our circle doesn't really look very circular. But if you count up, you can see that we've got 6 units across this way and 6 units across this way. So it really is a circle. It's just a problem with the way I changed the scale of our grid. So our center looks to me like it's right there. 0.60. We can go ahead and write that in. 60. That's the center of this circle. Now we're going to have a circle after dilation centered at the origin with a scale factor of 2. Now, remember our dilation is centered here. So we're going to have to take every vector from here, from the origin to the circumference of the circle, and double it. Well, I've drawn our dilated circle, which doesn't entirely fit on the page, but that's okay, because we don't need the whole circle to answer these questions here. Sketch the image, we just did. Well, most of it anyway. How are the coordinates of the center of the dilated circle related to the coordinates of the original circle? Well, for instance, the center of the original circle is 60. The center of the dilated circle is 12, 0. So the coordinates doubled, which makes sense. It was a dilation factor of 2. And it's true for all the coordinates. For instance, this is 6,3 here. This is 12,6. And down here is 12 minus 6. And way off the page to the right there is 18,0. What about the circumferences? Well, if we doubled everything, remember the linear parameters usually move right along with the scale factor, whereas the areas usually move as the square of the scale factor. So let's see what happens here. We've got a radius of 3 for the small circle and 6 for the big circle. So we get 2 pi 3 for the circumference for the small one and 2 pi 6 for the larger one? Well, everything cancels. That becomes 1/2, right? So if this is area of the small circle, and this is the area of the large circle, the ratio is 1/2, which means, doggone it, I wrote area. That's supposed to say circumference. Hang on. And we have that circumference for the large circle is 2 times the circumference of the small circle. And if we try that with area, I bet we'll get something similar. Let's find out. We get pi r squared. That's pi 3 squared, or 9, times pi 6 squared, or 36. Well, pi's cancel and we get 1/4, don't we? Well, that's the area of the small one over the area of the large one. Well, this means that the area of the large one, do a little rearranging, equals 4 times the area of the small one, which is the square of our scale factor. So just like what we expected to work out. And if you're on a test and in a hurry, I think you could probably just write down 2 and 4 without doing this. On the other hand, it didn't take long to double check, so it's up to you. Now here's one where they tell us ahead of time what the ratios of the areas are. And it's in a 2:3:4 ratio. And they give us the area of the smallest one. So let's say this is the medium tray. What about the area of the medium tray? We'll call that A sub m. Well, that must equal 3/2 of the area of the small tray. In other words, they're in a 2:3 ratio. So 2 times A sub m should equal 3 times A sub s. Which makes sense. If A sub s was smaller, you take 3 of them to make up 2 of these. Now what is A sub s? 483. So we get 3/2 of 483. This one's pretty easy. So for the medium tray, in fact, we can just write these in, right? This is 483. Medium tray, 724.5. Now, we also need the area of the largest tray. Now that we got these two, there's 2 different ways we can do it. We can use the ratio of the medium to the large, or the ratio of the small to the large. I think this one's easier because one's just double the other. So it's real easy to see from this that A sub L, so I can put it down here. No. Block this off. A sub L equals 2 times A sub s, or 2 times 483. When I multiply 483 by 2, I get 966. And of course, this is centimeters squared, and this is centimeters squared over here too. Next, they want to know about the perimeters. Well, they gave us the ratios for the areas, but remember, those would be the squares. In other words, if the ratio of the medium to the small is 3:2, actually it's then the ratio of the scale factor would be the square root of 3 over the square root of 2. In other words, for the perimeter, so the perimeter of the medium one would be the square root of 3/2 times the perimeter of the small one. And this number is still greater than 1, so far our equation makes sense. We're going to get a number here for this median perimeter a little bigger than this one. What does this turn out to be? So if we do our calculation here, square root of 3/2 times 80, we get 97.98. They wanted it to the nearest tenth. Well, this rounds off to 0 and brings this up 1, so to the nearest tenth, it's 98 centimeters. And for this one, to the nearest square centimeter. Well, so I guess I shouldn't have put the 0.5 in here. I should have made this 725. That would be the nearest centimeter, wouldn't it? Yeah. So, actually, they didn't ask for tenths in this one, so the correct answer here would probably be, by correct, I mean the full credit answer. I mean, anybody who didn't give you like 95 to 99% credit for this, I'd argue with him. Come on. So what if you didn't round it off? You gave an exact answer. What's wrong with that? I don't see what's wrong with exact answers, other than they're harder to write. Anyway, 98 would be the perimeter for this. So for perimeters, we get 80 over here. We get 98 over here. What if this turned out to be 966 on the inside? That's the area. What will the perimeter be? Well, let's see here. We have 2 to 4. So we multiplied the small one by 2 to get the large one. So now we just have to multiply. We get P sub L, the large one, should be the square root of 2 times the perimeter of the small one. And when we perform, this is 80. Root 2 times 80 is 113.14, or 113, wait a minute, they want it to the nearest tenth, so it's 113.1. This drops down. At least that's what my calculator came up with. So the only thing you had to do for this problem was remember how your ratios work. That's pretty easy. And then you have to remember that linear parameters will move according to the scale factor. Areas will move according to the square of the scale factor. Since they gave us the ratios of the areas, what they really gave us was the squares of the scale factors. So we had to take the square roots when it came time to find a linear parameter such as circumference. Now they've given us a rhombus with a circle inscribed and a little bit of information. The information they gave us is that this diagonal has length 6. This diagonal has length 8. Now they want us to find EF. That's this side right here. Well, what do we know about a rhombus? Well, all the sides are congruent. It's kind of like a square that's just been pushed over a bit, right? Well, we also know that the diagonals of a rhombus bisect each other, so we can immediately write that this side is 4 and this side is 4, and over here I can write 3 and 3, and just forget about these for now. 6 and the 8. We got 3, 3, 4, 4. Well, we also know that the diagonals of a rhombus are perpendicular bisectors. That means this is a right angle here. They ask us to find EF. Now we have two legs of a right triangle, which are 3 and 4. Now we could take 3 squared plus 4 squared and get 25, take the square root and get 5. But by now we already know that 3, 4, 5 is a standard common right triangle. So when we see 3 and 4, we can put 5 right up here for the hypotenuse, no problem. So we got 5 right here. That's EF. Now the area of a rhombus. Well, our formula for the rhombus, that uses diagonals, doesn't it? That's 1/2 d1 times d2. Or these are our two diagonals. But they gave us that, didn't they? 1 is 6 and 1 is 8. So we get 6 times 8 is 48 over 2. So we get an area of 24. Now what else? Down here, they ask us to use a different, use the formula for the area of a parallelogram, which is a little bit different. For a rhombus, we can use diagonals. On the other hand, since it's a parallelogram, we can use that formula also. This xy here, it's perpendicular to this side, because these are tangent and this is a diameter. Well, it might look more like an altitude if we were to move it over here to E and then drop it down to a perpendicular here. So we're taking the perpendicular distance from this side to the vertex here. That would be the altitude. That will have the same length as xy, because it'll be parallel to xy in between the same two sides. So we've got xy times EF. That would give us the area of a parallelogram if we knew xy, which we don't at this point. But we do know that this is equal to 24. Now they say find xy. Well, gee whiz. EF was 5, right? We've got that right up here. So xy has to be 24 divided by 5. And that's 4 4/5, or 4.8. Well, if xy is 4.8, maybe it'll fit in here. Find the area of the inscribed circle. Well, xy also is a diameter, which means the radius is 2.4. Let's not get confused with this. 2.4, they wanted the area, right? Yes. Times pi. And if we actually plug that into our calculator, and we get 18.1 square, no units, just square units. Okay. Next they say explain your reasoning. I'm not sure what there is to explain. I mean, the diameter was 4.8. Half of that is the radius. That's the explanation. And the area is pi r squared. So I guess your reasoning is that the radius is half of the diameter. Good reasoning. It definitely is. So the important parts of this problem, in fact the really important part, was to remember that for a rhombus, the diagonals are perpendicular bisectors. Without that, you're kind of dead in the water with this problem. But once you spot that, things are real easy. They gave us measurements. You can spot this as a right triangle. In fact, it's a 3, 4, 5 right triangle. And then you can, if you remember your area for a parallelogram, you can write this out, get xy, and do everything else pretty easy. I think the hard part was probably remembering that these diagonals are perpendicular bisectors. And then don't forget your formula for the area of a parallelogram, which uses the diagonals. So you just had to remember a whole lot about the diagonals of a rhombus to work this problem. Here they gave us a couple of concentric circles. That means they have the same center. And they want to know the ratio of the area of the smaller circle to the area of the larger circle. They gave us JL, which is 6. They gave us KL, which is 2. So JK must be 4. So area, the ratio of the smaller to the larger. Well, looks to me like that would be pi 4 squared over pi 6 squared. The pi's cancel, and we get 16 over 36, 4 over 9. And was that one of our answers? Let's see. Oh, here we go. See? All you got to do is subtract. If you know how to subtract 2 from 6, get the smaller radius, and then take the area of the larger one. This was a pretty simple problem. All you got to do is know how to get the areas of the circles. You know, this is one of those problems that probably looks a little rougher than it is. I mean, the biggest stumbling block you might see right off the bat is they don't give us any dimensions here. We don't know what any of these lengths are. But they want us to find a probability that something lands. Oh, I see. We're not placing something on it. We're removing something on it from it. So if we choose a point randomly from this diagram, what's the probability that it came from inside this little right triangle? Well, they didn't give us any numbers, but they gave us some stuff to work with. For instance, this here and these two squares, they're congruent. So we know that, in fact, we can put it in. This is a square, so we can immediately do that. But the squares are congruent, so we can do that too. So now, basically almost every single side we have, except for this one here, is congruent to every other side. I have a feeling that's going to help, don't you? So let's call the length of this side x. As you say, we got like 8 of these that are all x, and one that's something else. Are we going to need this? Maybe not. After all, we're really concerned with areas here, aren't we? So, what's the total area of this whole thing? Well, I would say that this square is x squared, and this square is x squared. So we could immediately write down 2x squared for these two. And what about this? Well, that's just half of one of these, isn't it? We know that because these two legs are exactly the same. Or we could just say that, use our triangle area, which is the leg times the altitude divided by 2. Or x squared over 2. Well, let's put these all together first. 2x squared plus x plus 1/2 x squared is going to be 5 over 2 times x squared, or 2.5 times x squared. That's the total area here. What we want to know is the probability that we took it out of this one, which, as we know, is exactly the same as the ratios of this area to the entire area. Not the leftover area, the entire area. So, in the numerator, what we need is this part here, x squared over 2. And in the denominator, we need the whole thing, not this part. The part left over, no, the entire area. That's 5/2 x squared. Well, if we rewrite this, we get x squared over 2 times 2 over 5 times x squared. Well, looks like we didn't have to know any of these dimensions, did we? Because they're dropping out. And the 2's drop out, and we get, well, they cancel. These cancel and the 2's cancel. We get 1/5, and that is exactly like 0.2, isn't it? So it turns out we didn't ever have to know what the actual side length of anything was. So when you see something like that, don't throw your hands up in the air, think you can't do it, because you don't have enough numbers. Just start working out with what you have, or start working it out with what you have, and see where you end up. And it wasn't until we got all down to the bottom here, where we're pretty much done, when it became apparent that our x's were going to cancel each other, and we never needed to know what they were. This one's it's pretty easy as long as you remember how to get the area of a parallelogram. We've got two of the sides are 300 feet, so maybe we can just draw ourselves a quick picture. A quick bad picture. Now if I finish these off here, this is like this, and this comes down like this. So that's there, and this part shouldn't even be here, should it? So this is 300. Our perpendicular distance. That's the part that we need, not this. So they gave us what we needed to. That's cool. It's 150. So if we get the area of this thing here, divide it by 5,000 square feet. Let's call 5,000 square feet a super acre. It's not an acre, it's a super acre. Really big. If we divide this area by 5,000 square feet, we'll get how many super acres we have. And it costs us $14 per super acre. By the way, I made up the term super acre. There is no such thing. Don't tell your friends that 5,000 feet is a super acre. They'll think you're nuts. So what is the area here? 150 times 300. And 3 times 15 is 45 with a bunch of zeros after it, right? So we get 45,000. What we have to do now is divide this by the size of a super acre. And that equals 9, doesn't it? Yeah, all these things cancel. 5 into 45 is 9. Well, now we just have to take 9. That's how many super acres we had, times 14. And let's see, that's 90 and 36 is 126, I think. I better double check that. Yeah, my calculator agrees. And that's in dollars, of course. So, I surely should have said 9 times $14 here is $126. That's our units this time. So again, this is pretty easy. You just had to think in units of 5,000 square feet, because we know how much 5,000 square feet costs. If you didn't want to do that, you could take this number here, 14, divide it by 5,000 square feet. That will give you your price per square foot. Multiply that by 45,000, and you will get the same answer. If we looked at it that way and got our price per square foot, which is 14, divided by 5,000 square feet, multiply it by 45,000, what are we going to end up with? Well, we got 45,000 divided by 5,000, so we're back to 9 here. 9 times 14. Well, so you could have done it either way. And the idea of writing this down was to show you that algebraically you're doing exactly the same thing. Here you divide by 5,000 first and then multiply by 9. You think of it as two separate equations. Here you find this, or write this out as your cost per square foot and then multiply by the whole. But either way, you can see that you've done algebraically exactly the same thing. Well, this is certainly a small problem. Let's see if it's also an easy problem. What have they told us so far? ED is 2. Okay, that's this one down here. ED. AB equals BC. That means that this is a bisector. Not a perpendicular bisector, but it bisects this segment. And they tell us that this whole thing is a square. Well, that's certainly going to help, because each of these sides is 2. Like this is 2, this is 2, this is 2. That means if we bisect this, this is 1, and this is 1, and AF equals FE. That means this is a bisector, so this is 1, and this is 1. Now they want to know, what's the area of the shaded region? Well, I would take the area of the shaded region to be the area, I'm going to call that the area of the diagonal region. Well, that should be the area of the square minus, well, if I call this triangle 1, T1, and this triangle 2, then this would be, we have to take the whole square, subtract off the area of triangle 1 and the area of triangle 2. So if we take the whole square and subtract off this triangle and this triangle, what's left will be the area of that diagonal strip. Well, sounds good. Let's see if it works. What's the area of the square? It's just 2 squared, or 4. What about this triangle here? Oh, that's pretty easy. We got a right triangle here. We know because they told us it's a square. And we got a leg and an altitude, so we have to subtract 1/2 of 2 times 2. And what's this one? Well, 1 times 1, isn't it? And we're going to take half of that, so that's just minus 1/2. So this is 4 minus, well, those cancel, so that's 2, or 4 minus 2.5, which I think would be 1.5, right? Yeah, so the area inside here is 1.5. You really didn't have to remember too much to do this problem, other than how to get the area of a triangle, and that's about all you really needed to know. Now that I get down to it, they tell you that that these two are congruent, so they're cut in half, and they tell you that these two are cut in half. You have to know that half of 2 is 1, perhaps, although your calculator could have told you that too. So you didn't really need to know very much other than this part here. To get to this odd-looking section, you take a nice, simple section that you can find, like the square, and subtract off 2 other sections that you can find. And that, what's left over is the part you were looking for. But basically, I'd say that's a pretty easy problem. Yeah, there's one that doesn't look too bad. Might be a little bit tricky. Let's see. Do they give us any information? Let's see here. The circumference of each circle is 8 pi square units. Okay. What is the area? Well, PQ here is 1 radius. And we're given that the circumference is 8 pi. So let's call this R for now. What the heck? And we should get that 2 pi R equals 8 pi. Well, let's see here. The pi's cancel, and we get that R equals 4. But the diameter for each circle is the same, meaning the radius for each circle is the same. We can draw, since the radius from, say, P to the circumference of this circle is R, well, this is the center of Q right here, so the distance from here to the circumference, that's also R. And they tell us that these sides are tangent, so the distance from here to this side is also r. They touch right there. They share that point. And we get the same thing here. This is also r. On the other hand, this side is tangent, and this is tangent, and they just touch, so that means that distance all the way across here, this is r, and this is r. So what we have is 2r this way, and 3r this way. I want to know the area of the square. Well, it's going to be 3 times 2, or 6. Area of the square is going to be 6 r squared, or 6 times 16 if I haven't made any mistakes. And we get 96 for the area of this rectangle. And again, this one was pretty easy. Just keep in mind what tangent means. They share this one point on the outside of the circle. That's how you knew that this side was 3r going this way and 2r going that way. And as long as you can remember your formula for the circumference of a circle, you can plug it in, get the radius, and then everything falls out pretty easily. Well, here's one using one of those game show type spinners. And do they give us any information on this one? Oh yeah, sure. They tell us that the diameter of the circle is 7 inches. Okay, that's probably good information. The arrow is spun until it stops. It's equally likely to land anywhere. If x naught here, if x degrees is 45, what's the probability that the arrow points to a red sector? Remember, these are supposed to be 2 straight lines here. The boundary between the pink and the blue and this boundary, these are straight lines, which means this is a vertical angle pair. So if this is x, then this is x. And they're both 45 degrees. Well, I say that the probability of landing in the, well, they said red. Okay, I'll call it red if they want. Probability of landing in the red sector is exactly the same as the area of the red sector over the area of the whole circle. And remember from previous problems when we worked this out, this is pi r squared times some fraction. This is just pi r squared. The pi r squareds drop out. And all that matters is the angle here, which tells us what fraction of the circle it makes up. Well, this is 45 and this is 45, so 90 degrees of red means 90 over 360. And that's all you have to do. You could take this, multiply pi times 3.5 squared divided by pi times 3.5 squared, and you would still get 90 over 360. So let's just do it this way. And you get 0.25, I think. Or in terms of probability, they frequently rate that as 25%. It's not really necessary. I don't think, anyway. I never saw anything wrong with writing point anything as a probability. I always thought percentages were more for business people and politicians who want to make arguments. Percentages are fun to throw around. What about the second part? When it says explain, well, I think this is the explanation. Our explanation is that we have learned from other problems that figuring out what proportion this is of the whole does not depend on knowing the radius. We only need to know the angle. You want to change the spinner so the probability that the arrow points to the blue sector is half the probability that it points to the red sector. Okay. Well, that means we can just write out exactly what it is they're saying, that a sub y over the total area, I'll just write it as a. The blue sector is the y degrees here. This is y and this is y. Well, that's supposed to be equal to 1/2 the probability of landing in the red sector, which is the area of the x's over the whole thing. Well, okay. And it's supposed to be an x there, not a y. There we go. Since we already know it only depends on the angles, we can immediately write that alpha sub x over 360 equals 2 times alpha sub y over 360. Well, we can just forget the 360s now, or multiply through by 360 on each side. And we get this. Well, if alpha sub x is 2 times alpha sub y, we can substitute. What equation are we going to substitute this into? Well, take a look. They are supplementary. We could write x and y is 180, or 2y plus 2x is 360. I'll just do it this way. And write that alpha sub x, this whole thing has to be 360, and then we can substitute. So, for instance, alpha sub x plus 1/2 of alpha sub x equals 360. Well, this is easy. Now we've got now I'm using alpha sub x and alpha sub y to represent the entire region here, both x's and both y's. So when we get done, we're going to get an actual answer, and we're going to get an answer that doesn't have to be multiplied by 2. We could just recognize that this is 180 degrees and write that this plus this equals 180 and get exactly the same answer. Well, we get half of what we would get the other way, and then we have to double it. I figure we'll just do it directly, where alpha sub x is the sum of these two, and alpha sub y is the sum of these two, and they have to add up to 360. And alpha sub y has to be half of alpha sub x. Well, if we do that, we would get 3/2 alpha sub x equals 360, or alpha sub x equals 240, and right down here we get that alpha sub y equals 120. Well, that means that this part would have to be, let's see here, 120 and 120, and this would be 60 and 60. In other words, you'd have to draw these quite a bit differently. These would come in here like that, and then your x's would be way bigger out here. This would be the red part out here. So really the most important part for this problem was to remember that probabilities work just like the ratios of the areas. If the area is 1/4 of the total, then the probability that you will take a point from that area is 1/4. As long as you remember that, everything else fell out pretty easily. You just have to remember how to do your algebra. You've got something as 2 times something else, so you write it out this way, make your substitution, set up an equation that can be solved. In this case, the two of them have to add up to 360. So I guess you had to remember that the whole circle was 360. But again, you didn't have to remember very much for this problem, except this part here. This was sort of the key to the whole thing, I think. And also remembering that you don't need the entire area for probability calculations, because when you're taking the ratios, most all the stuff drops out except for the alpha over 360 part. Well, for this one, probably the first thing we have to remember is the area for a kite. Maybe that's the second thing we have to remember. Maybe the first is the definition of a kite, where the two adjacent sides are congruent. So this is a kite. Diagonals of a kite are perpendicular. The diagonal, which runs from the vertex formed by the two congruent sides, bisects the diagonal which joins the two non-congruent sides. That is, the vertex formed joins the vertices formed by the two non-congruent sides. None of that might actually matter in this case, but we still need to know the formula for the area of a kite in terms of its diagonals, and that is 1/2 d1 times d2. Well, they tell us that d2, the long one here, is 3 times d1. So we can rewrite this as 1/2 of d1 times 3d1 equals 54. Well, that gives us the 3/2 d1 squared. And that's, I'm using this km for d1. This here I would call d2. Well, that equals 54. So we just have the d1 equals 2/3 of 54 and the square root of all that. Well, we can save our calculators a little work here if we spot something right off the bat. 54 divided by 3, let's see, is that 54? Yes, it is. Well, shucks, does that work? Oh, it does, okay. 54 divided by 3. We get 1, and 24 divided by 3 is 8. So this is 18 times 2 is 36. So what we really need here is the square root of 36. That's 2/3 of 54. 1/3 is 18 times 2 is 36. And of course, that equals 6. So this part here is 6. They just told us this was 3 times it. So this is 18. I think that's what they asked us up here. JL and KM. Okay. Now we have that another quadrilateral is similar and has an area of 486 square meters. And then find NQ. I guess that's the long diagonal. Actually, we could find both of them exactly the same way. We could, there's more than one way to do this. This is all from part A, so let's section this off here. We already found a formula. It's right here, but it's a different area. This works for this kite. Would it work for the other kite? Well, sure, because everything moves with the scale factor. The sides get multiplied by whatever the scale factor is. We don't really know what it is. All we know is that the new area is this. And we could find the scale factor by taking 486, dividing by 54, and then take the square root of that, because the squares move as the square of the scale as the square of the scale factor. Well, that's one way. On the other hand, like I said, we already have a formula here. If we believe that the diagonals change exactly the same way the sides do, and the fact is, they do. That's part of similarity. All the parameters move together. So if on our original kite, this diagonal is 3 times the length of this one, our new expanded kite, if it's a proper transformation, and they say it is, because it's a similarity transformation, they say that these two kites are similar. That means the diagonals have to be in the same ratios also. Just as when we perform our similarity transformation, these two sides are still going to be congruent, these two sides are still going to be congruent, and this diagonal is still going to be 3 times this one. So we can immediately just write down the formula we already figured out from part A. Seems to me and this will be our new D1, we'll call it D1 prime, I guess. This doesn't change, so it's still 3/2 of 486. Well, I wrote that backwards. No, I didn't write it backwards, I wrote it upside down. D1 prime is 2/3 486, and we have to take the square root of that. So if we do this, we get the square root of 324, which is 18, and that'll be D1 prime. That'll be our short diagonal. And our other diagonal, well, D2 prime, that's just 3 times 18. And that would be 54, which we already know because we had we know it's 54. So our diagonals for our new transformed quadrilateral are 18 and 54. If we had done it the other way, we would have gotten, I think, a scale factor of, between the areas, of 9. The square root of that would be 3. And so we multiply our short diagonal by 3 and get 18, and our long diagonal by 3 and get 54. You can do it either way. Well, that's it for the review.